Okay, so we have here Ghani. He's a professor and head of Department of Computer Science at Strathclyde University. And he's going to talk about open games and how the categorical foundations of open games work.
So thank you very much. First of all, I'd like to thank the organisers for inviting me. It's fabulous to be here amongst such excitement and such ideas, and I think in particular it's great to see how progressive these ideas are about changing the world for the better. Can't leave it up to the politicians at all. Before I start my talk, I also want to just tell you a little bit about us. So we're the MSP group at the University of Strathclyde. Our research group does categories, types, functional programming, dependent types, open games, string diagrams, and co-algebra. So yeah, it's great to be here. And so you're all welcome to come and visit us, and we'd love to hear from you. So please drop us a line if you're ever in Scotland or if you're ever in Britain. Do let us know. Come and give us a visit. And also, I'd like to point out that we're almost 10 years old. We're 9.5 years old. So we're planning a workshop July 2018 on the beautiful Scottish island of Islay, which has 4,000 people and 10 whisky distilleries. So nice. If you're interested in these topics, come along to Islay and mix them with some whisky. So I'm going to talk about open games, like I said. So open games are an attempt to do, for game theory, what compositionality has done for a lot of other subjects. So I'm not going to explain to you again the merits of compositionality. Many people have already done this already. It's regarded as best practice within computer science. It is just what you have to do. If you're not doing it, you're doing it wrong. But the thing is that in game theory, this is very, very difficult. And I want to point out in my talk why it is difficult. Even since the advent of game theory from the 1940s with John Nash, it's been known that it's difficult. And I'll show you some of the things that turn up. And also what I'll try and do is I will try and highlight how that difficulty has manifested itself in things we've had to invent in order to develop a compositional theory of game theory. And I should say also, when I'm talking about game theory, in computer science, in theoretical computer science, in programming languages research, there is something called game theory, and I'm not talking about that. I'm really talking about economic game theory, and in particular, the hard nut to crack, the thing that we're working on, is the idea of Nash Equilibria. So a subtitle for this talk would be A Compositional Theory of Nash Equilibria. That's what we're named after. And I think the motivation is very important. You hear a lot about smart contracts. In my opinion, these contracts are not smart. These contracts are stupid. They do whatever they're told to do. There is no analysis. What they are is distributed. They are autonomous. There are no central agencies required to execute them. So that's great. But that to me is not smart. They're not intelligent. They're not saying, is this a good thing to do? That's what Nash Equilibria does, and I hope that we can use some of our compositional theory of Nash Equilibria to make the work that you guys are doing smart, in the sense that there will be some situation that you can say, this is a great thing to do. This is the optimal move you can make. And then that will give your software an edge over all the dull software, which is just saying, do whatever you like. Okay, so to motivate this talk, I'm going to start off with the simple motivation question. So let's say we've got a set A of actions, and then some values that might arise, and a function which assigns to every action a value. And what we want to do is say, what's the best actions we can make? What are the optimal things we can do? Well, the equilibria, you might say, well, it's those actions which give you a value such that no other action has a better value. That's a very common, natural thing to write. So let's write that down. So it would be those actions, A and A, such that for all other actions, A prime and A, f of A is at least as big as f of A prime. So you notice this order means that V has some order. I'm going to ignore the order stuff, it's not that important. Okay, so that's a perfectly good definition. Everyone happy with that? What's upsetting you?
Seems a bit difficult to use in practice.
Welcome to economics.
Well,
So,
I mean, this is called argmax. That's just argmax there. Difficult to use in practice. No, have you tried using homotopy type theory? This is not difficult to use in practice.
No, in the sense
Have you
that,
tried using set theory?
in the sense that A, as if it's a set, it doesn't have a lot of structure, so
Okay.
I suppose you miss a lot of context.
Okay. So of course, I'm going to talk about sets and functions, but of course, we are implicitly wanting to work generically, so we can work in an arbitrary category. So these are just objects and these are morphisms. But for the moment, I'm just going to talk about sets and functions. Was that the only objection?
Yeah.
Okay, that's fine. Yes, of course, it should be categorical.
I was just going to, so V is a poset and we're picking out max model.
Yeah. But in general, as I say, I'm going to kind of avoid talking about the order structure, and we'll see that in a moment. Okay, so that seems a very reasonable definition. So now let's think of two-player games. Okay, so now we've got A1 and A2, our actions, that player 1 and player 2 can make, and V1 and V2 are values we get. And so we have what's called a utility function. So that says, let's say they make two moves, A1 and A2, and then they get two values. Okay. So, it's a perfectly good set or object, perfectly good, and it's a function, perfectly good. It falls into this setting. So this definition, which looks cool, which looks good, is it appropriate for these games? Well, the answer is clearly no. Because if you use this, you look for a pair of moves which maximize the value. But the thing is that A1, they don't really care what happens to A2. They're interested in their utility. So we're not trying to maximize V1, V2. We have two goals. A1 is trying to maximize V1. A2 is trying to maximize V2. So this approach is wrong. So this idea of just using argmax everywhere is wrong. It's just not the right thing. So this observation is what led Nash to introduce his notion of Nash Equilibrium and win his Nobel Prize. So what he pointed out was actually a better definition in this setting for a two-player game is a Nash Equilibria for that utility function. Okay, R. It's a little bit of a formula, but if you get the intuition right, the formula is obvious. So it's a pair of moves such that. Now, if A1 is going to be happy with, if player 1 is going to be happy with little A1, that means no matter what player 2 did, sorry again. Now, A1 is going to be happy with move little A1, no matter, if they try and change it, they won't get a better result. And simultaneously, player 2 must be happy with A2, so if they try and change it, there won't be a better result, assuming that these are the same. So in other words, we want to say for all A in A1, pi 1 of F of A2 is bigger than pi 1 F of A. You see? So player A1 is thinking about making move A1, little A1. So they calculate their utility. Of course, they're only just in their utility, so pi 1 takes the first projection. That must be, sorry, too many commas. And that must be bigger than, well, A1 might change their move to little a, and then they will get this utility. So the utility they got from playing A1 must be bigger than the utility they got from A.
Should we quantify your A2 too?
Okay, well, yes and no. In a moment, because of course you have to say and. So for this to be an equilibria, not only must A1 not to change their move, but A2 must not want to change their move. So for every A and A2, so for every other move that A2 could play, the utility that A2 gets from choosing A2, which is this, must be greater than equal to I2 F of A1A. Okay, so it's a little bit of a a bit of a formula. So basically, let's go again. So A1 and A2 would be the equilibrium if there's no incentive for either player to change their move. So for player 1, they could consider changing their move to A, but the utility they would get goes down. And player A2 could consider changing their move, but the utility they get goes down. So that's the Nash equilibrium, that's the definition, that's the formula. It's worth saying that not every game, this set could be empty. And if you look at the canonical examples, like the prisoner's dilemma, there is no equilibrium. Okay.
Matching pennies does not have one.
Right, matching pennies, sorry.
Rock, paper, scissors.
Well, you can imagine there are games where you think, oh, I could do this, that might be better, but then the other player could do something else, and that might be better. There's no particular reason these things should exist. So in some sense, optimal moves, optimal equilibria, they may be quite rare. But that's okay, you know, they're very valuable if they are, so we should hunt them down, and when they do exist, we should find them.
Maybe you should also mention that if you play probabilistically, they
About it, yeah. So the key theorem that's in Nash's work is to say, okay, in general, these equilibria don't exist, but if you play probabilistically, so you don't choose a move, you assign, oh, I'm playing that move with some probability and that move with some other probability, then you can show that these equilibria exist. That's the key famous theorem. Okay, so it's a great definition, and it's spawned 70 years of research, and it's continuing to spawn plenty more research. And it's a great definition because it fits our intuition. Yeah, that looks sensible, that's what we want. Neither player has any incentive to diverge. But it's not a compositional definition, it's not built up from smaller things. So the point about the work on open games is to say, yeah, this kind of stuff is good, but if every time we make a more complex situation, we have to scratch our head and write something down with ever longer formulas, you know, we're going to get stuffed. So we need to go back and try and address this compositionality issue. And so for that reason, we came with open games. So I'm going to now talk about open games, but I'm going to talk about it in two parts. I'm going to do a simple cut-down version to demonstrate that compositional game theory is possible, and then I'll introduce you to open games in their full form.
So, right now, are you saying that Nash FG does not equal Nash of F, Nash of G? Is that?
Yeah. I mean, there's nothing here about argbanks.
Yeah.
Well, I guess there is. I'm saying something like that. But actually, let's just hold on. We'll see what I'm about to say. So I'm not going to go quite onto open games yet. I'm going to talk about what I call simple games, which is simple but compositional model of game. Okay. So let's slightly change our definition of what a game is. So a simple game.
Neil,
Yeah?
could you say a little bit more about what you mean by compositionality in this concept?
Okay. I want
What
to
does it
build.
mean for a game to be compositional?
Okay. So, first of all, it means something for a theory of games to be compositional. A game does not make sense to say, is this game compositional?
Right.
The theory of games is compositional if I give you a definition of a game consists of this stuff. And there are plenty of definitions you can choose, so you have to choose one. I'm going to give you a simple game notion, and I'll give you a more complex one. And to be compositional, I then need to equip with operators to build new games from old ones. And like I said at the beginning, this is going to be difficult because whatever I choose in, there's going to have equilibrium involved.
But is it just that, or do you also want, for example, if you want to calculate the Nash Equilibria compositionally then?
Oh yes.
You want to have a local computation which composes nicely to give you the glue.
You'll see in the course of the talk what we get. But the answer is yes, because any of my definitions to be game theory will have to have a notion of equilibrium. And then we'll have to compute the Nash equilibrium of a big game from the components. Because that's what operators do.
It is kind of functoriality in some sense.
Well, functoriality, I mean, this is functoriality is a technical term which you might say says that things on objects extend to things on morphisms. So, in some sense, yes, if you set up the games as morphisms. But if you set up the game... Huh?
The game's not more.
Well, let's just carry on for a while.
And to be clear, in general, you can't compute Nash equilibria. There's algorithmic hardness results that just says it's impossible in general.
So yeah, so I want to stress again, yeah, this is not the thing that happens everywhere, and it's not an easy thing. It's, but if it does exist, this is a good way to try and find it. And there's motivation for trying it. Okay, but anyway, let's go to a simple theory of games. So a simple game is given by a set A, a set of actions, or categorically an object, set of actions.
Yes.
The values. And something else. So previously I had a utility function, which had type A to V. I'm going to change that. So I'm going to have an E. And what's its type? It says
E stands for something else.
E stands for Equilibria.
Okay.
But I'm not. But you know, as we see, we're going to stop being obsessed with argmax, and so I'm making it abstract. And with this definition, it's just a set, a function. We think of it as the equilibria, but you know, it's just an abstract thing. So if you look at the type, we're certainly going to say we return a set of actions. So in that sense, it's the same as we had before. But it's more general. I'll give you a set of actions which are in equilibrium for every function from A to V. So these are utility functions. So what I've done is I've taken away from normal game theory where you say, here's my game and here's my utility function. I've abstracted away the utility function. So I'm now, the price I'm paying, one of the first changes is, I'm going to have to deal with every single utility function simultaneously. That's the price I'm paying. It's a good price, in fact. And it's a small price. This is just a set. It's just, you know, we do functional programming. We don't mind having functions. But it's a higher order function. E takes a function as input. And that's part of what I was saying to, in response to Jules' question before, that if you want to do compositionally open games, you're going to study equilibria. If you make this step, you're going to have to be compositionally dealing with, you know, higher order functions, and this is more complex. You know, the A and the V, one of them is going to be occurring contrarially no matter how you set it up. It's a difficult thing. Okay, but there's my definition. So I've taken the normal definition and I've decided to index my equilibrium predicate by the utility function. Okay, so I'm going to produce an operator on simple games. It's going to be called tensor, so it looks a bit like parallel product. So I'm going to write down the parallel product of two of these simple games. So, well, let's do the obvious stuff. If we're playing these two games in parallel, we expect the actions to be the pair of actions and the values to be a pair of actions. And then what are the equilibria? This is the only hard thing to do. Well, the equilibria takes as a utility function. So let's give it a particular utility function. And because we made these choices, the type of the utility function will have to be this. Now I want to make it compositional. So just as the actions in this game are built from the actions of the individual games and the values, the equilibria must be built from the equilibria for G1 and the equilibria for G2. That is what will make it compositional. Equals. Okay.
The liquid strength.
Yes, courage, courage, courage. I'm doing this from my head rather than from slides. If I was taking on slides, I'd say, you know, I'd spend 1 second quickly grep the formula and then explain the formula to you. But now I have to. But it's a good challenge. Anyway, so I have to now, and this is why types are great. They tell you what you have to do. I've got to give you a set of actions. So again, it'll be a set of actions. Okay. Right. Okay. So now if you think about it, if I'm going to do this compositionally, I want A1 to be in equilibrium. That's, you know, I mean, all I have is A1 and A2. These are the actions. So I want A1 to be in equilibrium, and I want E2 to be in equilibrium. And at this point, if you're a classically trained traditional economist, you should rub your hands and wait for me to fall over flat on my face, because I'm obviously going to screw up. Because, you know, in a complex game, where I've got two moves that are going to be in equilibrium, it's not just as simple as, you know, this is not equilibrium, this is not equilibrium. You play a complex game, they interact. I mean, it's not as simple as this. You know, remember, this is a different Liouville sign. So what's going on here? Well, so A1 should be in equilibrium. So for G1 and for G2. But now the strength of the abstraction that I put in kicks in. Because I have to say not in equilibrium, full stop. I have to say equilibrium for a particular function. And this function is not this function. This doesn't type check. G1 has types A1 and V1. So I need a function from A1 to V1. So I certainly can't write K here. But I can write, let's take an A1 as input. Let's take A as input.
Can you inject and project?
Yeah, well, you can do whatever you like. Let's see if we can do something appropriate.
Your K looks like an R, by the way.
My K looks like this one.
Yeah, I also thought it was an R.
Oh, was it a K?
It's a bound variable. Okay.
K is for continuation, just as K.
And that's lambda A.
Yeah, so this is a lambda. So I'm assuming you all know a little bit about functional programming. This is how we write down functions. I need here, the type of G1 tells me I need a function from A1 to V1. So I write down my function by saying, let's take in an element A of type A1, and now I have to give you something of type V1. Well, of course, I'm going to have to use this K. K will give me a V1 and a V2, so I'll take out the first projection, because I only care about V1. And then I can apply K. And now I need K requires an A1 and an A2. Well, A1 is the thing that the first player is worried about. Oops, sorry. We're taking in an A. So that's the move for A1, and the move for A2 is fixed as A2. And similarly here, this will be lambda A, and now this is in A2. And it's pi 2, because we want the second version, K. Now A1 is fixed, we know the first player is doing that, and now we are considered playing A. Okay, so to answer Pavel's question, I claim now this is a compositional theory of game theory. Why is it a theory of game theory? Because I've given you a notion of game with equilibrium, with a notion of equilibrium in it. And why is it compositional? Because I've given you an operator that will build you new games from old. And in particular, I'll solve the problem of how to write down the equilibria for the complex game in terms of the equilibria for the simple games. And this is difficult. It starts off in a surprising way. You know, there will be a pair of moves which each is an equilibria. But I've solved the riddle of how I'm going to do this by noting that the utility functions change. So this is what you get in index programming. Those of you who you know, natural number index types and stuff like that. You index your data structures by some information, and then you use your data structure, but at other indexes. It's a very common thing in dependent type theory. Okay. Now, if you look at this, you'll see that actually, if we take the simple game of a one-player game, S at A, values V, and argmax as the equilibria, and another one, and we do this, the answer we get is the Nash Equilibrium. So that tells us, I mean, here is a formula that type checks, but that tells us that this is the right answer. And in particular, Nash Equilibria now are no longer a primitive, atomic, empirically justified concept. They are now a derived concept from the structure. So that's very good. So we've got a compositional theory of game theory. Wonderful. Where the equilibria for the complex game is built from the equilibria for the simple games.
So this looks like some kind of categorical structure. Is there a way of diagramming out what this is doing?
Yeah. So I mean, there's a tensor. You know, you know what's going to happen.
Actually, this is a question I also have. Like, you talk about compositional games now, but you are using the tensor symbol.
Yeah.
So is this the formalization of parallel composition.
Yeah.
And so we need also the sequential.
Yeah.
Okay.
So this is all right, and this moves on. Actually, a great audience. I was heckling, but in fact I'm getting support. This moves on to the next part of the talk.
So if you stop here, these things form a monoid.
Yes, exactly. If I stopped here, I'd have a monoid of games. I'd have a set of games and a structure on it, and I guess I'd
You have
find
to
it
prove
unique.
it's associative.
What's the identity?
The identity.
Oh.
It would be, well, you'd have to have one element
One,
set,
one.
one element set, and the equilibria would, I guess, say that that one
Is an
element is an
equilibrium.
equilibria.
That's
The utility.
that's the zero play game.
So it's a game where nothing happens, you just stand still and look at the ceiling.
Well,
It's a game with no players.
Even better,
So-
an
so-
empty room.
And one move. And like a move you can make with no players, like look at.
Yeah, it's an empty room, right?
Yeah.
Chessboard with no one around. Okay.
right. What time should I finish talking? What have you done so far?
20 minutes.
20 minutes talked or 20
I think
minutes
you
left?
talk 20 minutes with this keep going, it's fine.
Okay, so in fact these are great questions. So, I've said I've done a compositional theory of Nash Equilibria. Jules has pointed out the abstract structure I came up with as a monoid, and all of you should feel a little disappointed. And Fabrizio quite rightly said, well, this is like parallel product because you get pairs of moves. This highlights the problem. It's compositional, but the operators I have are not very expressive. I only have one parallel product. I mean, I don't even know to do basic games, I might find some basic games. But the key problem that's missing is sequential composition. You know, if you want to do monoid categories. But also just from the practicality, we want to do sequential games. So, and you just can't do it with simple games. And so this motivates going to open games. So just to recap, I gave you simple games because you get a simple taste of what you need to do if you want to do compositional game theory, generalized equilibrium predicate. But they're too simple. So to do sequential composition, we're now going to do proper open games. Right, and in order to motivate, I must admit I have a small brain, and my brain can cope with about 6 symbols. And an open game has about 7 symbols. So I always found it a bit difficult, and I was kind of, oh, if only I could use fewer symbols, but 8, even worse. So therefore we're going to take it slowly. If I just wrote out the definition, you probably would have the same reaction as me, especially because you haven't studied them for 2 years apart from so we're going to take it slightly more slowly. So previously with our games, we had some action, or if you like, a move. And then we had some value, or utility. So consider, so here's my here's my example, which I always use. So I'm an amateur gambler. As an amateur gambler, I place bets. But if you think about it, I don't just place a bet. I have to go to a bookmaker. Would you like to be my assistant? So I have to go and say to you, hello, I'd like to place a bet. And you say, hello. And you say, very good. And you take my bet. Of course, how much I bet will depend on various things. Particularly how much money I have. It might be I live in a country where you can only place bets if you've got a positive bank balance, for example. So I also have a state. So let's have a state. And also, I'm just going to introduce some more ideas. I could, for whatever reason, be feeling, optimistic. I could bet large amounts of money. I could be risk averse. I could bet small amounts of money. So I'm going to have some strategies. And these are the strategies we're going to try and optimize. That's the thing we want to know. What's the best strategy? And if you notice, in this more complex situation, I'm distinguishing the strategy from the actual action or move. This is the observable. This is what is going on inside my brain. And I can control this. It's different from state, because I can't control this. I can't control my bank balance, I think. Okay.
Unless you're a hacker.
Yes. Yes, you're a central banker. But now this is the crucial part. I mean, that so far is fine. This is the crucial part. So I go to you, I look at my bank balance, I think of a strategy, and now I play a move. I decide to bet on something, and I go to you and say, I'm going to bet on this. So what do? Well, your state is going to be the bet I choose. You know, whatever it is, that's the state. So let's have this here. So when you do the sequential composition, you know things match up. And what matches up is the output of my activity, my move, matches up with the state of the recipient. And then you've got various strategies as well. You could decide, you know, you always win money off me, Neil. I don't like you. Go away. I'm not accepting your bet. Or you could take the bet. Or another thing you can do is you could place it. You could, you know, place it with another bookmaker. So you also have your own strategies. And then, of course, you know, something else happens. So maybe the race is run, or something like that. And then, as a result, you will expect some values. So you get some value back. You know? Now, this is the key point. After you get some value, how do I get value? You give it to me. So the result you get needs to get fed back here. But you don't just give me this back, because you might take your commission or whatever it is. So here's a new concept. In order to make open game theory rather than closed game theory, when I, as a component, gain utility, I need to gain it from somewhere, from the environment. In this case, from the bookmaker. My winnings come from you. So we introduce a new concept of co-utility. Utility is what I receive, but all economic agents, not only will they receive utility from their actions, they also choose to extrude utility so they can be gained from somewhere else. It's like you know, it's a conservation of utility. If I'm going to win, somebody has to give me my winnings. So you see, we've got a new type here, and this is co-utility. And then this gets fed back to me, and then of course, you know, I might also, for whatever reason, have someone above me in the chain. So of course,
that's your loan up there.
Yes, I may pay back some of my loan. Indeed, yes. There's the bank up here that's giving me my money. Yeah.
Probably A's, like you already used A.
Oh yeah, I've always used A. And I've screwed up my lettering. It's not the usual lettering we use. So on this board, I'll re-letter. But what you can see is we've got a slightly more sophisticated situation. So now, again, an open game is, okay. Previously, a simple game was a 3-tuple, set of actions, set of values, and an equilibrium predicate. And now it's MFOI. For the reasons I've tried to explain about having to have co-utility, it's not more complex. So I have X as a state, signal strategies, Y is moves, we tend to use R, utility, and S, co-utility. So there's 5 bits of data to do with the sort of with the state and the utility and the co-utility and the moves. And if you like, there's definitely a forward direction going down here. You know, you look at your bank balance, you think about what you might do, and then you get to move. And then there's a backward flow of information, where the utility from your action arrives after it's been out in the environment and various things have happened, and then later on you extrude some of that as co-utility. But also, there's a play function, which takes a state and a strategy and gives you a move. Co-utility, so this takes a state and a strategy and some utility that you've won, give you some co-utility. And finally, the equilibrium predicate, which says that in a state and with a utility function, certain strategies are in equilibrium.
Why do you have an R in the definition of C?
Right, because how much money I extrude depends on how much money I win.
Oh, okay. Yeah, reasonable.
Yes, it's obvious.
That's
I would
slightly
say-
more mysterious why it would depend on X.
Yeah,
It's slightly more mysterious why it depends on X or sigma.
well,
We started out life as a mathematical trick.
Yeah. So let me state, of course, so this is open games, and this is a definition, and it's been successful, and I'll explain a bit more about what that means. But it's not the only one. It's not clear this is the right one. So, for example, Jules, and I trust him, he always works with best responses rather than equilibrium. Change this. More radically, where do you put probability if you want to do things like this? If you want to study probabilistic systems. And you might need to change the definitions. I don't want to talk about it, but that's another thing. And finally,
in that case, it's not sufficient to change P of sigma with some other monad, probably, or stuff that is there.
So that's in fact that's in fact what we are. That's in fact what we're doing. P for probability, but you've done something different. A probabilistic game is no longer an open game. It's a different thing. You know, and after debating it for a long time, we've agreed upon this. But that means all the work I'm going to tell you about open games has to be redeveloped for probabilistic open games. If a probabilistic open game was just an open game where the set of strategies was P of sigma, I wouldn't need to redevelop anything. But I think you get the wrong answers. So, oh, I want to say one more thing actually. Those of you who like dependent types, and certainly Fred in the room in yellow, and those of you who've done index containers and structures like that, will say, well, maybe these types are very unconstrained. You know, the set of strategies available to me should depend upon the state. In some state, I'll have these strategies, but in this state, I'll have those strategies. And in that case, you don't need to write the x, because the sigma,
like a dependent pair.
the sigma now is type x to set. So for every state, you get a set of strategies, and now you can just write P as type sigma arrow y. So the types actually become much nicer and become much simpler. So that's another thing that at Strathclyde that we are toying with, and there are some motivations for doing it.
Why do you no longer need the sigma and c?
Sorry?
Don't you still need sigma and c?
Yeah.
Well, no, because now the R. So just like
right.
just like the strategies.
Yeah.
So again, the R encodes the information of the state.
And it's probably the more realistic and more applicable setting for most economics.
Yeah. And also mathematically it will be better. I mean, using dependent types to make the types actually line up means you don't have any of the stupid things where you try and take the tail of a list and it's an empty list.
And
or you take the product of two things and actually you have to pad something out. There are all sorts of errors from not using precise dependent types.
That's the same reason for using battery nets and like dependent input types, which you need to specify depending on which transition.
So that's a future line of research which we think works and it ties in lots of things. We should do it, but you know, it's just.
Could we quickly review the concrete meaning of these three functions?
Okay. You mean in the non-dependent type version or in the dependent?
Yeah, none. Just for now.
So this thing was a set. Right. So play. So this is just data. Nothing's happening. But in order to have a game, I need to actually make a move. So P says, if you're in a state X, and if you choose a strategy sigma, what move are you going to choose? And then C says, if you're in a state X and you use a strategy sigma and you win R, how much of that are you going to give away? And then the equilibria, well, it's the same as before. Give me a utility function which translates moves to utility, and I'll tell you which of those strategies you consider to be equilibria to be best for that utility function. And I put the x in here because everything depends on the state. So,
can't you choose the best strategy also according to your co-utility? Like if you are a bookmaker, isn't your strategy dependent more on your co-utility than your utility? Like you don't want to be bankrupt, so.
You could do, but I think that's a mistake because I think the thing is, you know, utility. What is utility? It's almost by definition the thing we want to optimize.
Okay.
You know?
So you say like co-utility is somehow implied by your utility.
Well, they're clearly related.
If you know your strategy and your state and your utility, that's enough information to know your co-utility.
Yeah, okay, yeah, that's okay.
Yeah. these are modeling assumptions, you know. You could make 12 tuples, you can have more refined games, you can make simpler structures independently, but there are variations. Anyway, but that's an open game, as we did. And of course, I didn't do this earlier, I must give credit. So this came out, I believe, in collaboration with Jules and Philip. It's Jules' thesis. I'm sorry, Victor and Philip. I joined that, I first heard about it maybe 2 years ago now, where I thought, wow, this is cool. You know, this is, you know, because I've been going to this conference called Logic and Social Behavior, and lots of people using category theory, and Zarev's theory of various things, and Samson Watson was going to these things. And, you know, it was all fine, but then I saw this, I thought, this is, you know, this has nailed it. I mean, this really, if you look at this and you think, you know, this is Nash's equilibrium done compositionally. So then I got involved, and now there's a lot of people in Strathclyde, and there's people in Leicester working as well. Okay. How much more time do I have, Yellow? 5?
Yeah. Mate, honestly, as much as you want, this is still cool.
Well, I'm proposing tomorrow, as soon as we don't have talk slots, to talk for a potentially infinite amount of time about this for anyone who wants to listen.
Okay.
You don't need to talk infinitely fast.
Right.
It's actually a common finite time.
So I'll tell you some of the stuff we've been doing. So, a new notion of game. More sophisticated than a simple game, we have to develop compositionality for it. So we have to write down, first of all, parallel composition that we had before. So, X, I should say, and now we're going to also start being more categorical. So, we're going to type such a game as XS, G, Y, R. And you'll see why I've put the X and the S here, the Y and the R there. It's to match up the composition. You'll see that when I do composition, but I'm just going to do parallel composition first. So if I have an X prime and an S prime, and a G prime, a Y prime and an R prime, then I need to write G tends to G prime. So this should have, it's like playing the games in parallel, so you start doing the obvious things. So the moves should be an X and an X prime, and each of them are going to add co-utility, and you get a pair of moves and a pair of utilities. And then the play function for this game should take a pair of states and strategies, that's right in here, and a pair of strategies, and you have to get a pair of moves. You can just do that point-wise, and you chunder through and you write down the right things. The type checker will help you, and the equilibrium predicate is much like what we saw before. It's very Nashian flavour, but it is compositional. So that's parallel composition. For sequential composition, so we have one game, and now we have another game, H, 2 and 1 R, Z, T, so we saw here that the interface we do the composition on are the moves and the utilities of the first game, which are the state and the co-utility of the second game. So that's why that's typed. That's the thing you match on, so that's the thing that has to go there, rather than here or here. Okay, so now let's have a look. So I'm not going to write down the full definition. It is just a nice thing. When you've got your mathematics right, and you're required to write down a function, everything falls into place. You need an X, you only have one X, you get it from there. You need a Y, you've got a function that produces a Y. You need all just press repeat on the algebra. But I'll write down the play function, for example. So the play function for H after G, by definition, should take the state for the composite game, and a strategy for the composite game, and the strategy is a pair of strategies, and give you a move. Right, so you get the state from the first game, the strategy for the compound for the sequential composition is the product, and now we need to make a move for the compound game, which is a move for the second game. So how do you do that? Well, the obvious way. Well, we have to first play the move in the first game. So we need a state and a strategy for the first game. And that gives us a move in the first game, which is a state in the second game. So then I can take the play function for the second game, use the state, and give it a strategy, etc., etc. And most importantly, I have to write down the equilibrium function for the sequential game. So this would require a state for the first game.
Quietly skipping over code play.
Yes, quietly
It's really
skipping over.
difficult.
Yeah, I mean, it's like, you go through one game, you go to the next game, you have to come back up, and then up again. So, I mean, the geometry is fine, and it's accurate, actually, because it reflects the process. I mean, if we have this, the betting example, and I wonder how much money am I going to give out in the composite game, well, what do I have to do? I have to use my co-play function. I need to know my utility. What is my utility? I have to use your co-play function, because that gives you your co-utility is my utility. So again, you see how the co-utility function, not only is it natural empirically, where does my winnings come from, you have to give me it, but also it fits in the types. Okay, so then the equilibrium for the compound game. Right, so when is a strategy, that's sigma 1, sigma 2, in equilibrium for the compound game, in a state, and for a utility function k, and this should have type, so the type's your friends, it takes a move, no it doesn't, yes it does, it takes a move for the compound game, that's a z, and it gives you a utility for the compound game z over t. Sigma 1 is in, 2 is in, e of g, e of h. And I don't have time, so I'll let you fill them in. But it's the obvious thing, you can type check it. I mean, here I need a state for the first game. Oh, I've got a state for the first game, so I'll write that down. But now I need a utility function for the first game. And here I need a state for the second game, I'm not sure what that is, and a utility function for the second game, and I do have k.
Yes.
So the formulas are slightly longer than one would prefer, but they do capture the sort of mechanics of this interaction.
And again, the intuition is that it's some kind of Nash equilibrium.
Pardon?
Again, the intuition is that
Yes.
it's really like an unrestrained Nash equilibrium and Nash equilibrium with synchronization in the middle.
Right, so it's right. So I could write down anything here, of course, the type checks, but it has to match up with some kind of idea of practice. So the Nash formula doesn't cover the situation, but it sort of appears to be right, because when you look at the utility function, you see that each of these agents are going to maximize against something. But what's worth saying is, in this situation, if you look at this point, I've made a strategy for the overall game to be a strategy for the first game and a strategy for the second game. There's an alternative. So in economic game theory, they often talk about sub-game perfection. Okay? And sub-game perfection is all about, well, various things could happen, and I want to make not one equilibrium, but a choice of strategies for each of these possibilities. And in this setting, you might say the second player has the option to look at the move that the first player is making.
So it becomes a function there.
Exactly.
Yes.
So there's a different composition, where the strategies for the composition, certainly a strategy for the first game, but a function from moves of the first game to strategies for the second game, and then you have to thread it through.
And I suppose that this becomes a more general case of the previous one.
Actually, this becomes so. And you think about it more, and the best thing is to leave composition alone. But this becomes a more special case of choice. If you,
Oh yeah, because you're restricting your strategies to looking at what happens before, while in the other case you're just like, I'm a rebel, I don't care. Okay.
Yeah. So to answer Pavel's question, I think what we're seeing is different operators build in different information assumptions of who sees what and when, which is vital. So we need this expressive calculus of many operators to build in the different situations which we're trying to model. So that's sequential composition. So I'll finish with saying two things. So now, of course, we have an idea of games like this, and this is a nice model category, so you can do your string diagrams. As Jules was pointing out, you have your cup, and you can write one down, that's fine, but you don't have a cap. So this diverges from traditional compact closed models of string diagrams. It's just that this is economics and it's different, so it has different structure. I'm quite cool with that. And so in some sense it'd be nice if your general theory wouldn't always give you compact close, but would allow you to choose how much time reversibility there is.
So what is the cup?
The cup?
Yeah.
Okay, so let's say you've got a game which ends XX. What we want to do is produce another game that ends 1 and 1. Because that 1 is when you're closed.
I don't understand how you can end XX. One of the X's is supposed to be an action, the other a value.
Yeah.
A result. So what does it mean that both of them are the same?
If the thing that you care about optimizing is the move itself.
Yeah.
Oh, okay, I see.
So, for example, in a special situation, you make a move X, you know, but you might want to, but the value you get is an element of X. This is very general. That's fine. So the cap. See, if I write the cap here, tau, then this tau has type x comma x to 1 comma 1, as you'd expect. So what it's doing is, you know, you've got this environment which is going to translate your moves into values, and actually, in this situation, the cap is just saying your move is your value. It doesn't have to be that. In some situations it isn't.
It's like karma.
Well, it's just tying the loop together.
Yeah.
And I'll just give you the type of the game. It's obvious what, you know, you just write down the functions, it's obvious what it is. And then you should try and write the other one, and you'll see there's no natural economic interpretation that you can write down. So we have our monoid category, we can do string diagrams, we have a cup. Now, what we've also done, that's sequential composition, that's parallel composition. We've done choice, sort of. That's a collaboration between, I mean, we've done some of this stuff, and Jules has independently done some stuff. Choice is important, and that's why I also know how to represent choice in a string diagram. We've also done final coalgebras, sort of. And that's nice, because we can do iterated games. So now we can say, here's your prisoner's dilemma, now, apply the operator, you get your iterated prisoner's dilemma. And I mentioned situations like, you know, can we prove a theorem which says, and we discussed this once, we failed to finish it off. You know, if you've got, we can try and prove theorems in this framework, like, if you've got a move that's optimal for a one-shot game, is repeating that move optimal for an iterated game? And the answer in general is no, but maybe we can say something. We can also be really cool, ask an economist what an iterated prisoner's dilemma is, and their head will explode, because it's not compositional. But this is just two operators, this is a double final algebra, so it's quite simple. Hopefully true for us. But inside all of this work, you're building complex games, and you want to build the complex games as with universal properties. And now if you thought about it, you'll suddenly realize this structure won't do that, because here the games are morphisms. So actually, you need, between two different games, we need morphisms of games, so that the games can become objects, so they can have universal properties. And this is very difficult because the contravariance in equilibrium predicate. So this is ongoing research, and unfortunately we have two answers. One works in one situation and one in the other.
We're having a professional disagreement. We each have a pet way to do it. Very compatible.
Even worse, one of them works in one situation and another in another one. So, and it might be up to more general. You know, the contravariance, relational algebra, something like that might be needed.
So you're now in a situation like general relativity versus quantum mechanics.
Yeah.
Both works, but you have to choose.
Yeah. Okay. So let's see. So that's no problem. So I think that's a good place to. That's roughly where we are. We have a compositional model game theory that's expressive. We can do sequential composition. We can do parallel composition. There are other variants using dependent types. Maybe there are more operators that we need, although I think we've got a good core calculus now. Choice, infinite iteration, finite iteration, and parallel and sequential composition. It's an open question as to what the morphisms of these games are. So it's quite an active field now, lots of room. And I would say, you know, it's more than we can do, so we are very grateful for any help you can give us. And the final thing is, I guess, we're just poor old mathematicians doing what we think is beautiful from a categorical perspective. What we really need is real world problems. So again, the idea of looking at the problems you have, taking your Petri nest, taking real problems, that's what we've been crying out for ages. So thank you very much for listening.
Thanks.
Maybe can I think I disagree with something here. I'm trying to put my finger. So in some sense, the terminology is weird, right? Because on the one hand, you're calling X X is a state. The entire state is exposed to the environment, so there is no internal state. Your state is completely determined by the environment. So these games, they look, when you look at your play function, the way your play function looks, it looks something like innocence. Are these innocent games in some sense? Because there is no, these games don't have an internal state, right? Because on one hand you're calling X a state and you're calling Y an action, but they're really of the same type, right? In the compositional environment. So you're confusing the notion of states and action, which is cool. I mean, no, I really like it, but I'm just wondering if that's the right terminology.
The way we actually model that is when you actually build a particular game compositionally, you have part of the environment is a kind of continuing state of the player that's threaded through, which is not necessarily the best way to do it, but that's what we have.
Right. Okay. So basically, what you're saying is that
yes, it is innocent. They're innocent in that sense.
Right.
You have to manually do it.
And I guess I need to see some. I mean, it would be cool to have another talk with lots of examples, right? Because I guess I think what you're saying, Jules, is that probably the kind of decompositions you get are not maybe the obvious ones, right? You have to be a bit clever in the way you decompose games.
Maybe I think that it is certainly the case that when you have a language of operators, there are many expressions in that language which will determine the same semantic structure, open game, actually, whatever. And so certainly, while you might be given one of them, that might not be the best for the particular analysis and the particular problem that you want. And so the same problem that we discussed in your talk arises here. How do you choose? Which particular construction, compositionally on a particular game do you want? I think that's a fair comment, right?
Yeah, I mean, it kind of looks almost like some. I mean, there are things like mealy and more machines, right? So you have an internal state space.
Yeah.
You have an input, but here you have the data flow going in both directions.
Yes.
And there's this additional equilibrium function, which breaks the symmetry.
Yes.
This is why you have the
exactly.
the cuts on one end.
I can give you a more symmetrical definition that's much less obvious, or even less obvious.
And then maybe a word on that. So a precursor of this compositionality was a paper of mine with Achim Blumenthal. So that was it was kind of the pre-compositional thing because we have not managed to build equilibria compositionally. So the basic building block in that approach were co-algebras. And then you had exactly the kind of things, so the input in the media or Moore machine, whatever, was the history here, so the X, so the stuff the agent is observing from the past or the history. And then there was the internal state, like in a co-algebra, that was the state of the agent.
Right.
And
that's what's missing from this definition.
Yeah, that's exactly. So what we had in mind in that paper was really what we call the econometric agent. We are still one step before we are able to build in the econometric agent here inside. The econometric agent was meant to be an agent who is observing the world and then estimating in terms of in an econometric or machine learning sense, estimating some model of the opponent or his strategy, and then decides what to do. So that would be a learning agent who is just an AI agent somehow. And there you see clearly that there is this notion of observing the history and an internal state, which we call the epistemic state. And at some point in time, we would like to have this econometric agent here as well. So which, by the way, would be a very nice thing for a general AI and so on, because if you have a composite theory of composite games, you could build complex game and put the agent inside the game and let it run the game and let the agent learn. I mean, that would be the real cool thing.
But for that, you need some kind of econometric state.
Yeah, exactly. And I mean, co-algebra is exactly what it is. I mean, a co-algebra is a Kalman filter. That's the general process of estimating the unobservables from what you observe. That's one application of co-algebra. So all of econometrics and machine learning should be built based on co-algebra. So obviously it's the mathematics of observing, right? But it took a while to get the probabilities right, then these kind of things. But you're right. I'm in the same state. I'm kind of confused always between this discussion of states and histories Neil is doing, and Jules as well, and then sure.
On top, there are actually games which are based on states as well.
Yeah, it doesn't help me and Neil use slightly different terminology because I don't call them states, I call them observations.
Yeah. Well, that's what I would call them, so I agree with you.
Okay, I mean, I'm certainly, of course, not wedded to it as a good mathematician. It's the algebra that counts, not the names. I'm happy to do that. Do you have a question?
Yes. So related to that, you were talking about how there are slightly different definitions about the underlying assumptions into the definition of the game and how to define like the play, co-utility, and the equilibrium functions. So do y'all have any ways to relate between different formulations yet? Or do they, once you define one, it just relates to itself?
Yeah, no, I think the only thing we have is for the different notions. So we do open game, probabilistic open game, which is currently, in my mind, a different notion.
It is a different notion.
Yes. It's a twiddle, it's not much, you just put the monad in here, but it's a different definition.
You have to reprove the McLean axioms from scratch.
Yeah, and then the dependency type games is just to see what operators do they support, what does the algebra look like, you know, is it simple or is it hard, you know, it's very empirical stuff. I think that, you know, there are obvious clear tests. So for example, the notion of choice we have at the moment has the universal property of a product. And you can argue that's reasonable because it's actually a demonic choice, but you might argue that's because the types are wrong. If you use a dependent type, a more refined version. So, you know, there's a mathematical intuition as to what definitions are supported and what universal properties they have. So that would be one approach. And then the other is just, you know, can you define the operators? If you have a different definition to define parallel composition, sequential composition, and infinite iteration, you know, is it easy? Is it hard? It's just empirical stuff at the minute. I'm not even particularly sure what you can do. I mean, you know, if I give you two definitions or three variants of a Petri net, you don't say one's better than the other. You say, well, they have, you know, this one models time and this one, you know, builds in something, and they're all valid, I think. Some may actually not be as valid, but the general status you expect is to have all of them, many of them will be good at some things and not at the other, and they'll be strictly parallel.
But from a purely practical point of view, reproving the McLean axioms over and over again is a massive waste of time. But you really have to do it because quite a few, in the work we've been doing in the last 6 months on Bayesian open games, which are more complicated than merely probabilistic open games, like 6 different proposed definitions that we thought were the right one had the McLean axioms failed in various very subtle ways.
So I think
like
definitely some abstract algebra
fails to be natural or that kind of thing.
So some abstract algebra like you're doing. I mean, my feeling is, you know, this stuff is complex, it's contravariant, and it's a predicate or a function space. So let's just, we'll have to treat it out by hand probably for a while. But the rest of it, it's just a multi-sorted algebraic theory. 5 sets, 2 operations. You know, surely there's some general machinery that we can use.
So a very short and I suppose last question, because time's running around. So you talk about values, and at least in these, let's say, lesson, tutorial, whatever, you represented them as sets. But there are some times when basically, I suppose that when you say values, you have like numbers in mind, maybe. Like what happens?
Absolutely not.
What happens when you have like qualitative judgments on something, and how do you write equilibria and utility functions for this? Like I was thinking about, for instance, comparing different Petri nets formalism. And in that case, you don't really have any kind of measure. You say, this is good for these reasons, this is good for these reasons, which one should I choose? And how can you represent this?
First of all, let me reassure you, Fabrizio, I am a category theorist. I'm a card-carrying member of the category theorist party. If possible, I would stand for membership of the Central Committee. So when I write all this stuff, internally, I'm doing nothing about assuming the nature of these things. As a good category theorist, I don't look into their internal structure, so I absolutely do not think of them as numbers. These are abstract things.
So they are sets. They're like
no, these
objects.
are objects. These are objects in a category. Yes.
But it seems like you are assuming Cartesian closeness, because that's an internal home and that's a product. So we at least know something about the category.
You have to assume it's locally small.
But yeah. But I just mean like, Oh, well, isn't that an internal hump, the function?
No, it's an external. You can do it with an external.
Okay. Okay.
Yes, I could write C. But you know, I think kind of having just said that, I'm really excited about the applications. I don't want to spend my life on coherence and all the nitty-gritty stuff. So that's a criticism of myself. I'm not as good. I'm not as pay quite enough attention to the underlying structure that's needed. Providing I don't look inside the objects and I'm working in a kind of catalog or whatever.
The answer to your question is, if you're working composition, you eventually bottom out in the base case, which is, for example, a one player's single shot decision. And if your values are not numbers, then you have to do some work at that point. Say, what do you mean by automatic and short manual?
Yeah, exactly. Okay, yes.
So, I mean, you still have to put in what do you mean by automatic.
Yeah, exactly.
Maybe just related on this, the underlying concept, the model individuation and what he likes is a selection function. And the selection function itself actually has a qualitative nature because it basically says something is good or not. And of course you can exchange what is called a context.
Okay. Thanks again.
No problem.